So I wanted to go over another example of mechanisms. Um, we, uh, we studied two kinds of mechanisms. One has a slow first step. That's actually the easier kind to study. But this is a part of one of the second kind. It has a fast equilibrium first step. Okay. Um, so several things about mechanisms. First of all, we're trying to find, the mechanism should explain the rate law for the reaction. Here's the reaction, by the way, up here. It's A plus B plus two F's make E and G. Okay, a little abstract using just letters, but I think it's easier than all the writing we usually do. But one thing, and here's, someone might decide to write a rate law like this. K times the concentration of A times the concentration of B, let's see, times the concentration of F squared. Right? Don't say right, it's wrong. Well, it might be, we don't know. The thing is, you can't determine the rate law of an overall reaction like this except by going in the lab and measuring it, doing experiments. That's the only way. So, and my point is, you cannot in general just look at it and say, oh, A to the first power, B to the first power, F to the second power. You don't know that, okay? You can't do that for an overall reaction because the overall reaction is really generally a bunch of steps. And the rate is really determined by just one of those steps, the slow rate determining step. So we can't necessarily do it. We don't know this, okay? Let me tell you what experiment actually says about this reaction, okay? By hypothesis for this problem. Experiment says rate is rate constant times A times B times F, but only to the first power. Okay, that's what the experiment tells us. And whatever, if this is a proposed mechanism that somebody came up with, and it might be right, it might be wrong, but it had better do several things. And well, one is it's got to add up to the overall reaction, right? It's got to add up A plus B plus two F's form E and G. Does it do that? Let's see. C is intermediate, right? So if I added this up, it would be all the reactants, arrow, all the products. So we can kind of look at this and see if something appears on both sides, that would appear in the reactants and the products, and you can cancel them off. So C is formed there and used up there, so that's not going to appear in the overall reaction, and neither is D. These guys are intermediates, right? But it'll be A and B and two F's form. C and D are gone, but E and G. So then that's exactly what we have up there. So yes, this does add up. If you don't believe me, you can draw a big line, write all the reactants on one side, all the products on the other side, cross off anything that appears on both sides. It adds up. The other thing is, it's got to match the observed rate law. It's got to match the experimental rate law. Okay, and we'll show that here in analyzing this a little bit more. The last thing is, it should be all unimolecular and bimolecular steps, right? Because three things, the reasoning is three things colliding at the same time, A plus B plus C hitting each other, or A and a B and two F's all hitting each other at once is too improbable. So we want a mechanism made of unimolecular or bimolecular steps. So, right, how do we proceed? Well, one thing is, I've got little rate constants for each step. I've got K1 here for the forward first reaction. This is the fast equilibrium first step. We have to talk a little bit about what that even means, but there's a forward reaction and it has a rate constant K1. And just following your book, the rate constant for the reverse reaction, K minus 1, okay? So we'll talk in a moment a little bit more about that. What that actually is, a fast equilibrium, what's going on there. This is step number 2. Let me have a rate constant 2 there, sub 2. And this one, rate constant 3. And what I mean is let me put it below here because I'm going to run out of room. I'm board limited here. K3, okay. K2, K3, K1, K minus 1, okay. What is, say, the rate of this one here, number 2? You know, that's the rate of the overall reaction. For an individual step, I can simply write down the rates, looking at what are the reactants and that's all in other words, I can do this. Rate of number 2 is equal to the rate constant for number 2 times C times F. Hope you can see that okay. Rate number 2 equals K2, C, and F. And you say, well, didn't you just say you're not allowed to do it? You're not allowed to do that for the overall reaction because the overall reaction, it consists of a bunch of individual steps, one of which is slow. That's the rate determining step. You can do it for individual steps. By just like here, I can look at this one here, rate 3 equals K3 times D times F. And rate number 1 equals K1 times A times B. Okay, I can write the rates of the individual steps. It's easy. It's very easy. And how do we find the rate of the overall reaction? Well, that is, in this case, this is the slow step, rate determining. This rate number 2 is the rate of the reaction. The assembly line can only go as fast as the slowest step on the assembly line, right? The mechanism can only go as fast as the slowest step. The slow step determines the rate. So this is the rate. This is the overall rate. You say, well, it doesn't look like that, right? Doesn't look like that. It's got a little problem. We're not done. We're not done. Why are we not done? The problem is just C in here, okay? This rate, it is the rate, but it's expressed in terms of the concentration of C. And C is an intermediate. So what's wrong with being intermediate? Well, I can't exactly go to the stock room and get a bottle of it, can I? I can go and I can get some A and some B and some F, and I can go back to my lab and I can mix them all together and I can run this reaction and I can measure. Here, you're saying, how do I verify this? How do I verify that the rate is, you know, I don't have any C. It's just an intermediate. It's temporarily formed. Anyway, long story short, we don't like our rates expressed in terms of intermediates. So we want to find another expression for that. F's okay. F's one of the reactants, right? That's okay. But the C, we don't like. The way we do that is this, utilizing this fast equilibrium first step. And I said we had to talk a little bit more about that. What is that? A and B are getting together and form C. C is falling apart to form A and B constantly, going back and forth and back and forth and back and forth. That's why they call it a fast equilibrium. They're back and forth and back and forth. And what that does is it maintains constantly a pool of C. There's always, you got this reaction mixture going. It's forming an A and B and two F's are forming E and G, but in it, there's some C constantly present. In between being formed and falling apart, there's C present, right? You got this equilibrium. So there's some of this and some of that, and they're going back and forth. Every once in a while, one of these C's leaks away and goes through step 2 and forms then this last fast step also and finishes the reaction. But meanwhile, you have this pool of A and B and C, and they're interconverting back and forth constantly. Okay. And where we get the expression for C that we're looking for is we say this. We say that the rate of this going forward is equal to the rate of this going backward. That's like steady state. If that's true, then A and B are forming C, and C is falling apart into A and B, and they form a steady state situation with A and B and C. Okay. But anyway, that's what we utilize. This expression, we say if it's a fast equilibrium, rate 1 is equal to rate minus 1. You say, uh-oh, wait a minute, rate 1, we got that, K1 times A times B. And rate minus 1, we know, where's that? Well, we can write it down by looking, but you kind of got to stand over here and say, it's going this way now. It's as if C is the reactant, right? And it's K minus 1 is the rate constant. So what we'll say is K minus 1 C, okay? So if somebody flipped this over and asked you to write that, you'd say it's this rate constant times C, because C would be the reactant. That's what I'm saying. But you got to stand over here and pretend it's going that way. It is going that way, right? And so this is the expression that we can use. You see, it's got that C in it, and I could solve for that C and plug it in there, which is what I want to do. Easily done, right? Just divide both sides by K minus 1. K1 over K minus 1 times A times B is equal to C. And I wanted that expression for C because I want to plug it in here. This is the rate expressed badly because it's got the C in it, but now I have another expression for C and I can plug it in. So let me do that. I'll say the rate of the reaction, which is this rate number 2, right? The rate of the reaction is, let's not forget any of it. That's the thing that's easy. Okay, rate K2, C. That means I need all of this. K1, K minus 1 in the denominator, A, B, and that's C, and I'm done. No, because I still have F here. F. Ta-da, that's my overall rate, and it is written in terms of A, B, and F, which are the reactants, and I compare it to the experiment, and well, you know, if only I could call this K, this lump of K's, that would work, wouldn't it? I mean, these are constants. I don't really know what they are anyway, right? 3 of these constants lumped together equals that K. It does. It matches the experimentally determined rate law. So this is good. Big check mark by that. It matches the rate law. It adds up to the reaction. It's all unimolecular and bimolecular. We have a good mechanism. So I just wanted to do one more of those. Our process is always the same for these with the fast equilibrium step at the beginning. There'll be a slow step. You write the rate for it, but it's in terms of some intermediate because it's not the first thing, it's the second or third. So the reactants, one of them is the intermediate. How do you find out the expression for the you take the fast equilibrium step, set forward rate equal to backward rate, solve for the concentration of the intermediate, and plug it in where you need it. Anyway, thank you.